Couple more rules for finding antiderivatives, and you're going to recognize these as being really similar to their counterparts for finding derivatives. There's a sum and difference rule that says if I want an antiderivative of a sum or difference of two functions, I can find the antiderivative of each one and add or subtract those. There's also a constant multiple rule that says if I want an antiderivative of a constant times a function, whose antiderivative I already know, I can just find the antiderivative of the function and then multiply that by the constant. This now is going to open up all of the sums and differences of functions whose antiderivatives we can find, which is a whole new family of functions. Something like this, it's almost a polynomial, not quite. I'll do the first one the long way so you can see all the ins and outs, but please know that you know, if you encounter shortcuts or you can do some of the arithmetic in your head, that's okay for these. So let's see. The sum and difference rule says I can break this first integral up and do x to the 10th, and the constant multiple rule says I can put the constant on the outside. So I'm going to do both of those at once. Minus, and again I can put the constant on the outside. Just integrate the function, making sure to put that dx with each and every part. This is x to the 1/2, which I'll rewrite that way so I can use the power rule on it easily. So now I've broken this function that was the sum of three functions into three component parts, and I've put the constants out of the way on the outside. Now, these are all power functions, so I can use the power rule on each one. Got my 5 out here. Antiderivative for x to the 10th is x to the 1 higher power over that new power. And then I have minus 6 times the antiderivative of x squared is x to 1 higher power divided by that new power plus, and let's see, 1/2 plus 1 is 3/2 over 3/2 constant of integration. And we can do a little better. We can consolidate those. So let's see, 5/11 x to the 11th, and if you want to put 5x to the 11th, that's the same thing. 6 divided by 3, well, we can do that one. 6 divided by 3 is 2, x cubed. Don't want the complex fraction. 1 over 3/2 is 2/3, x to the 3/2, and then plus c. And there it is. And it is definitely okay if you're able to go from the top to the bottom without pass and go in between. My next one, and you can break this into two separate integrals if you want. I'm just going to realize that I could do that, and I'm going to integrate each one separately. The integral of 3 times 1 is 3 times x to 1 higher power divided by the higher power divided by 1. I'm not going to write that. Next, well, if this was 1 over 1 plus x squared, I know the antiderivative of 1 over 1 plus x squared. That's an arctangent. The constant multiple out in front is just multiplying. So this is 4 times the arctangent of x, constant of integration, and we're done. So sums and differences, constant multiples. Here's kind of a relative of those. If I want to integrate e to the 3x, we know that e to the x is its own derivative, so e to the x is also its own antiderivative. But if I just say this is e to the 3x, that doesn't quite do it, because if I take the derivative of that, I do get e to the 3x, but then the chain rule kicks in, and I need the derivative of 3x, which is 3. Similar to what we said with the power rule, we can fix constants. If it were just e to the 3x, I'd have this extra factor of 3. In order to counteract that, I can multiply by a third. And now, if I do the derivative of 1/3 e to the 3x, I get 1/3 times 3e to the 3x, which is 1e to the 3x, which is what I wanted. We're going to talk about functions like this in a more formal way eventually. But for right now, if you happen to recognize that the difference is going to be a constant, we can fix constants. So really similar idea for cosine of 2x. I know the antiderivative for cosine x is sine x, so this is going to be some version of sine of 2x. And I'm going to have my constant of integration. If I take the derivative of sine of 2x, I am going to get cosine of 2x, but I'm also going to get a 2 out here from the chain rule. I have to counteract that 2, that multiplication by 2, by dividing by 2. Like that. And again, we'll talk about the chain rule and how it works with integrals more formally in the future. But for right now, if you're off by a constant, we can fix that.